Hello and welcome back. So now we spent a lot of time teaching you how to construct logic and capture it in Verilog RTL. And we've also now spent a significant amount of time looking at how to approach high-level design, how to deconstruct a high-level target into a working and efficient structured design. Now what I want to do to finish off the hardware sections of this course, the implementation sections of this course, is talk a little more about design efficiency. At this point, I'm kind of polishing the apple. There's nothing terribly fundamental in this particular section, but it's some tricks and tools and techniques that allow you to get to more efficient designs. So typically when we talk about design efficiency, we have to think of what our design objectives are. They're usually some combination of throughput and latency from a performance point of view. Throughput being operations per second. Latency, how long does it take to complete a specific operation, whether it's an atomic one or a large one, such as completely decode a particular photo. And quite often, the design cost is measured either in power or area. Traditionally, we're concerned about area because that leads to implementation cost. How much does it cost to make the chip in the fab? But increasingly, we're concerned about power because our main limitation in many systems is how much performance we can get within the power constraints of the system. Typically, in a mobile platform, 2 to 3 watts. In a desktop platform, possibly 100 watts if you're using advanced air cooling. So they're the general objectives, but sometimes we try to summarize these in terms of a metric, which allows us to compare different designs, particularly in an academic course, where we're often not trying to meet a specific design objective. And the metrics that I've used in this course over the years are performance per unit area and performance per unit power. The former basically being performance per unit cost of silicon, and the latter performance within that you're likely to achieve within your power constraints in your system, which is increasingly the case. So in this section, what we're going to do is look at the 4 subtopics down the bottom here. High-level structure, mid-level, and low-level. This is going from the design as a whole through to the actual detailed logic. And then I'll talk about a few more advanced synthesis techniques that can enable you, within Design Compiler at least, get somewhat better designs. So first of all, high-level structure. Very, very often at the high level, your most significant constraint is memory bandwidth, particularly if it's off-chip memory bandwidth, particularly if it's 2 DRAMs. This fundamentally limits the performance of your system by what the technology gives you in terms of memory bandwidth. Thus, quite often, your design ends up being, how can I maximize the performance within a specific memory bandwidth? We saw an example like this in the motion estimator. We had a constrained memory bandwidth. It led us to rethinking the details of the scheduling of the steps in the motion estimator in order to make that memory operate at 100% capacity and maximize our performance while doing so. Next level of thinking about this is possibly thinking about the other logic units in your design and ask yourself the question, am I using this efficiently? Do I have blocks that are idle most of the time? Or even worse, replicated blocks that are idle most of the time. I mean, that would be a sin in terms of achieving maximum performance per unit area. For example, multipliers. Multipliers are relatively large, as are register files, as are memories. And if you've got lots of these units sitting around mostly idle, then you should really be looking at how to share them. For example, share one multiplier rather than build several multipliers. And these are often examples of good designs where a designer has thought through how to maximally use the large units in his or her design and has actually captured that in code rather than just blindly go and write code, which typically ends up leading to inefficient designs. Similarly, if you have a pipeline structure, how full can you get it? If it's mostly empty, you might not want the overhead of pipelining. Pipelining introduces additional registers, which increases area and increases power. So if your pipelines are mostly empty, you've got lots of bubbles in them, as a pipeline designer would say, then you might want to consider having fewer stages. Mid-level structure, we talked a lot about this in the timing notes. That is, rather than just having a flat piece of logic, consider pipelining it, consider opportunities for block-level parallelism, consider how to parallelize a serial critical path, retiming, that is, moving logic around between the flip-flops. Now, all these things we looked at that level in order as aids in order to improve the efficiency of a design. And remember, the parallelism aspect is very important. The intrinsic difference between hardware and software is software is intrinsically parallel, whereas hardware has massive amounts of parallelism available within it. In principle, every logic gate in your chip can do something every clock cycle. Then there's a low-level structure, which is largely using human-driven knowledge to work out better ways to do detailed logical operations. In the timing notes, we had a comparator example. Before, I have mentioned that sometimes, not necessarily all the time, but sometimes priority logic tends to have a deeper logic depth than non-priority logic. And remember, the difference here is if you can write a case statement and reorder the cases and it doesn't make any difference, then you have non-priority logic. If the order of the cases actually matter in the case statement, or if you have an if-else statement, then you have non-priority logic. Then you have priority logic. And finally, and we've seen this before in the comparator and in the register file, adding human-derived structure as to efficient logic implementations can make a substantial difference in the efficiency of that implementation, often at the expense of actually more code. These are less elegant solutions from a code perspective, but more elegant solutions from a hardware perspective. And isn't that what every engineer strives for? To achieve an elegant design that all your peers can admire forever onwards. Well, here's an example of such an elegant design. Here I have a simple arithmetic shifter, that is, I want to shift to the right by a variable amount and preserve the sign bit. And the way I do this here is I have 32-bit variables, so SC is 5 bits wide. I just create this longer temporary vector, not all of which we implement as hardware, but is the now 63 bits long, so that no matter how long the shift is, I will keep putting sign bits into the top of the unit. After the shift happens, it gets assigned to a 32-bit unit. In hardware, this becomes a rotating shifter, and in which the sign bit is preserved and propagated back through the shifter. Well, you can specify this and let synopsis loose, or whatever you design, whatever your compiler is that you're using. And what it'll do is it'll essentially just basically work out a truth table, work out a reasonable minimization for that truth table, and you'll end up with a big sea of logic, which won't look terribly regular, though this problem is kind of regular. And that's reasonable, and there's nothing particularly wrong with it, except it's not the most efficient way to build a shift unit. The most efficient way to build a shift unit is to recognize the binary nature of what we're doing and do the shift in a binary decomposed fashion. So here what we're doing is building a succession of muxes rather than just letting the logic optimization loose. This first mux here, the question mark colon builds a mux, is working out whether to shift by 1 bit or not, depending on the low order bit of SC. The second mux here is taking the result of the output of the first mux and deciding whether to shift that or the original, that by 2 bits or not, depending on the second bit of SC. And so on. You'd have to build 3 more of these in order to complete the shifter. And I'll give you a chance to do that in the X quizzes at the ends of these sections. Point is that this mux-based design, because muxes are generally quite efficient units, is quite a bit smaller and faster than just giving behavior, which in turn leads the design compiler to say this is the truth table, and it goes and tries to optimize the truth table. Instead, we get these smaller units that have human-derived structure on it and will look quite a bit more regular after the synthesis run, that lead to smaller, faster designs. So in general, if you as a human logic designer are aware of a method to make logic more efficient, you basically have to specify it. The thing you don't have to do are the Carnot maps and De Morgan's laws type of manipulation in order to try to make it more efficient. That is what synthesis is good for. What it's not good at is working out these intermediate structures. It doesn't have this human type of knowledge of what are useful intermediate structures for different types of logic operations, in this case a shifter being one of them. So that's one example of low-level structure, and there's many others like that. Fortunately, you don't have to be an expert in all the different ways to build logic. Quite often you can get these human-optimized designs from IP, or intellectual property, which we've talked about before. Here's a simple example. When you write plus in Synopsys, it actually builds a ripple carry adder, which, as you know, is a relatively slow adder. If you want or need a faster carry look-ahead adder, then plus doesn't give you that. You instead have to use designware, in the case of Synopsys, to build such a carry look-ahead adder from its intellectual property or IP library. If you want even faster designs, such as a carry save adder, in which you have 2 carry look-ahead adders and you pre-work out the solutions based on the specific carry bits that go in, and select the solution based on that carry bit. Look it up if you don't get what that is and you're interested. Then this requires human design. You'd actually have to take the carry look-ahead adder from designware and add the additional structure to it to build a carry save adder if you wanted this even faster adder. So these are all examples where human-derived knowledge can be useful to you to make a more efficient logic level design, but quite often this human-derived knowledge is built into existing intellectual property blocks, many of which might even exist within your company. Changing gears a bit and looking at more efficient synthesis, the first things here are the obvious things. You might recall at the beginning of the synthesis run, we set up these constraints. And all these constraints had to do with timing for your block. Now, how did I generate these constraints in that synthesis script? I made assumptions about what my logic was connected to. If it's not connected to what I assumed it to be, then I might be over-constraining, or even worse, under-constraining my design. If you're over-constraining the design, it'll tend to be bigger because the tools have to work harder and add more logic to make it faster. So getting these accurate is important, not just from a timing convergence perspective, but also from a design efficiency expected. If these are if these are too large, if the delay outside your module is larger than it actually is, if you're assuming the delay outside your module is larger than it actually is, then you're over-constraining your design, making it bigger than it needs to be. Another simpler example is operating temperature range. The fast and slow cells we've been using come from specific extremes of assumed temperature. And if you know you don't need to operate over that wider temperature range, then you can actually get a lot faster design by using that knowledge within the synthesis run. If you don't, now this slide isn't really about more efficient synthesis. In fact, from my viewpoint as an instructor, this slide, at least the first part of it, is about how to fix things if you screwed up. Remember, one of the things I talked about in partitioning was making sure there's a flip-flop in every timing path from input and out to output. Well, if you haven't done that and you insist on not doing that, then this is how you fix that. And that is, you actually have to hand constrain that delay from primary input to primary output using this max delay command. So that's how you do that if you insist that you want to structure your design that way. Similarly, and this is something that actually can make your design more efficient, there are various paths in your design. Actually, reset is one of them. But others where you have configuration pins that are set on day one and never changed, that coming into your design, which aren't intended to operate synchronously with the clock. They don't change at the clock rate. They change much less frequently. And again, reset is actually one of these. And if it turns out that one of these paths is actually entering your critical path, then you can actually benefit from telling the synthesis tool that this is not a synchronous path, it's an asynchronous path. And you can do that using this set false path command. And again, I'll leave a lot of these. I'll have to leave the details to you in the documentation if you choose to do it. This is another one of those things where I've pushed you not to do this, but occasionally you feel you need to make a more efficient design. And you do have to do this through your resynchronizing FIFOs as you go from clock domain to clock domain in any case. And that is when you have multiple clocks in a design. We always have multiple clocks, but they're tricky to manage. If you have multiple clocks within a design and you don't have the resynchronizing FIFO, then you might have to do something like this in order to move data between the clock domain. And that is, you basically have to say from between which pair of flip-flops, what is the delay? Now, it's not an arbitrary delay, it's one of these two clock periods. And you do that by saying it's a multi-cycle clock with respect to one of the clocks CP here. So what we're doing here, as we're moving from a faster flop to a slower flop, we're telling Synopsys that path can take 2 clock cycles in terms of the faster flop's clock cycle in order to complete that transition between those 2 flip-flops. And by using this, then you can manage multiple clocks going specifically between successive flip-flops. Again, I do suggest instead 1 clock per module. If you're doing resynchronization, have a synchronizing module in which you put in that FIFO structure I talked about in the timing notes to do that resynchronization. So both of these, max delay and set multi-cycle path, might be useful to you if you insist on structuring design in a certain way, or if you've ended up doing so and you just have a few of them and you need to fix it. If you have a lot of things that require this sort of fix, you can see this will get very, very tedious. Managing each path, individual path by individual path, as is going on in both of these examples. And that's why I suggest you avoid them. Don't have these circumstances appearing in your design. Okay, let's talk about some techniques to get the fastest possible clock speed. Generally, the way Synopsys suggests doing this is start with a clock that's pretty fast already. Don't start with a really slow clock. And the reason for this I mentioned at the bottom of the slide, and that is because the initial compilation is very important in terms of determining the final structure of the design. No matter how many times you recompile it later, you're only tweaking with the initial compilation. So initially you try to set a clock speed that's just achievable, but only just. You then look at the report timings, and in general you actually want to look at the 5 worst paths. You then tighten the clock with another create clock and execute a compile-incremental. You might recall that all compiles or logic optimizations after the initial one are incremental optimizations. Right. Don't start with no clock, and don't start with a clock that's way too tight or way too loose. If it's too loose, you'll start with a design that's nowhere near being as fast as possible and can't be tricked into being fast as possible no matter how many times you throw compile incremental at it. If you start with a design that's too tight, then you're going to end up with a design that basically doesn't work because you won't meet timing, and that will compromise, again, what logic you're starting off with. And what you do is you iterate on this loop, and I suggest you save the synopsis representation of the design in between iterations of this loop, so that if you need to backtrack, you read back in old implementations of the design. Because often going back to an old clock doesn't make it work again, even if it was working originally at that old clock. This works well if you only have a few paths that are creating setup violations. If you have lots of paths creating setup violations, there's another technique that complements this on the next slide. So again, this technique, we're looking at the 5 worst paths, and what we see is they're very close together. That is, yes, there's one critical path, but there's few other paths that are very close to being critical. And furthermore, they're intertwined with the critical path. So what can actually happen is, as you try to fix this problem through successive compile incrementals, all you're doing is moving the logic around between those critical paths and not actually fixing the problem. One way to deal with this is to tell synthesis to deal with these paths simultaneously by grouping them together as per this group path command here. Now what you're doing is giving an equal weight to all these paths, and 5 isn't a magic number. You actually have to work out how many paths are equally critical, or close to being equally critical, and use that number of paths. But now what you have to do is, is essentially treat this as one bundle, and you have a chance of getting better optimization out of it. And whether you've done this or not, the final arrow in your quiver to minimize timing, to minimize the clock period, is to throw a high map effort at it. You might recall -map effort tells Synopsys how long to run the algorithms for optimization. Synthesis is an NP-complete problem. It never actually finishes. So the question is, how long do you go before saying, I've done enough, let's call it a day? And -map effort tells a tool when to throw in the bucket. Low says give up easily, unlike most of you, of course. Medium is the default. And high is when, I'm close, I'm really close. And you throw high at it, let the computer run, possibly for many, many hours, and get back with a more optimal result. And finally, I do remind you, to a very large extent, your design, your code, determines the speed of the design. If you've done something ugly in your design capture that's created a bad critical path or a bad set of critical paths, no manner of tool massaging will fix it for you. You might have to go back and redesign it. That's speed. Let's talk a little bit about area. We've talked before about resource sharing. Here's an example. We have an if-else statement and 4 adds. And the point of this, because of the if-else statement, you actually don't need 4 adders. So if this statement is within one procedural block, not split up amongst many continuous assignments, then the synthesis will say, aha, you don't actually need these 4 adders. You can get away with 2 adders and a mux. So I will do that for you, work out that these big resources, adders are kind of big, can be shared. There's some limitations on this. If you're interested, look at the documentation. But again, if you do things quite naturally by specifying shareable resources within the same procedural block, you'll be getting this in general. Another example we had was in finite state machines. Remember, we grouped the next state logic and the output logic together because they actually shared the state vector decode logic. And even though it's not a resource sharing, their logic optimization is done better if they're in the same procedural block, at least according to what Synopsys says. A few other minor things. Check design can tell you if there's unused logic. Invariably, you will get reports of unused ports, and that's okay generally, as they're usually unused ports from designware blocks, particularly outputs. Are okay. Inputs, be a little more concerned about, because then you got floating inputs, which can lead to incorrect logic. Report resources, tells you about resource sharing if you're interested. The various techniques to try to force synthesis to produce faster logic. Set structure boolean be true, flatten it to 2 levels, another. These are in the library. And finally, and this is fairly rarely done, but finally, you can say, you could be there ripping your hair out, saying, synthesis isn't giving me the logic I want. Well, what you can do in that case is use the generic technology cell library. That's the generic cell library within synthesis. And you might have actually accidentally seen these if you've been using Synopsys when you've forgotten to do your .synopsys initialization properly. What this is a generic set of logic gates available within the synthesis tool, so they're always available. You can actually design in these gates. It's a netlist. You just specify a netlist using these GTEX cells. And you can hand optimize it down to the gate level. And then if you put a set don't touch on it, all that'll happen in the synthesis compilation run is they'll be mapped onto the actual logic cells in the particular library without changing their structure and rearrangement. This is basically doing hand logic design. So it's not very efficient from a design productivity point of view. But if you have to, well, you have to. But it is rare, and I've actually never encountered a case of it myself. Finally, I remind you, there is quite a strong speed area trade-off in most designs, particularly larger designs. As you crank up the speed, you're not necessarily improving the design efficiency in terms of performance per unit area. Or in performance per unit power. You are increasing the area and the power in order to crank up that speed. And this is because the basic technique to meet a faster clock is to put more parallelism into the logic at the micro logic level. So here's an example taken from the book referenced on the front. One design, the same RTL, baseline 65 megahertz, led to 1386 lookup tables. This is how you build combinational logic and FPGAs. We'll come back to that. And 353 registers, well, specifically flip-flops, I think, in this case. Make the design faster, the area goes up. You need more lookup tables and more registers. Quite often in FPGA, you're quite seriously constrained, particularly in the lower cost FPGAs, as to how many of these things you have. So this is actually slowing down the clock is one way to fit things better into an FPGA, as illustrated here. So that brings us to the end of this set of notes. I have some summary points. Just to remind you some things. How is performance measured? Throughput, operations per second, or latency, seconds to complete a specific high-level optimization, are the typical metrics. How is design efficiency measured? Performance per unit area, or increasingly today, performance per unit power are the common metrics. How do you do high-level optimization? You've got to exploit the parallelism of hardware. And one way to do this is through pipelining. Resource sharing matters as well. The mid-levels, it comes down to design before coding. If you've thought through your design and thought through how to make it efficient, then you'll end up with an efficient design. And the low levels, you can choose to add human optimized structure at the logic level to make a faster, smaller design. Use of muxes to build shifters, setting your order of your operations and the comparators and adder examples we have to make them faster, specifying structure within register files, another example we've had. So again, this is just a set of general polish issues about how to make a design smaller, faster, and quite often when it's smaller, it's more power efficient as well. And I hope these polished techniques are useful to you. But I do want to emphasize that the basic design principles in the sections that preceded this are very important and are your first order methods in order to achieve a good, fast, synthesized result. Thank you very much.